Okay, so this is the lab help file for Lab 4, which deals with probability. And in Lab 4, there are four parts. The first part looks at simple probability rules that were covered in lecture. Part B, you'll be using a binomial calculator to determine binomial distributions for three different farming conditions about growing cherries. Part C, you'll be using a Poisson calculator and the Poisson distribution to examine the distribution of tornadoes in Illinois to see whether it's random or not random. And then finally, part D, you'll use the normal distribution to answer some questions regarding some temperature data for Kamloops for one day, for June 29th. We've got historic data from 1901 to 2021. We're going to talk about that. One of the questions, we'll look at that 2021, because on that day, Kamloops broke a record by a substantial margin for the hottest day. So it's maximum temperature on June 29th, and the temperature that day was 47.3, an all-time record. So let's begin by talking about Part A. In Part A, you're going to use a table of data that is supplied in Excel format. And this data refers to degrees that were granted by UBC in 2019 for both campuses. Degrees being identified as either being undergraduate, master's, or PhD. And of course, this could have occurred in the Okanagan or on the Vancouver campus. And also, there's information on people getting these degrees, whether or not they were a domestic student, an international student, or an Indigenous student. So let's go back to the question sheet. And the first question asks, what is the probability that a student received a PhD either from the Okanagan or the Vancouver campus out of all the 2019 graduates at UBC? So the thing that's most obvious in this question is that the denominator in our calculations needs to be total number of degrees conferred that year in the whole UBC system. So 14,793. And the question asks PhD degrees for the Okanagan campus and for the Vancouver campus. So there we have total number of PhD degrees in Vancouver and total number in the Okanagan. So 46 over this number and 504 over this number. Now you need to figure out whether you're going to add, subtract, multiply. What do you do to get your final percentage to answer the question? The second question asks, what is the probability that an international student received a master's degree either from the Okanagan or Vancouver campus out of all the 2019 graduates at UBC? Once again, it's total. It's all of the 2019 graduates at UBC. So your denominator is still 14,793. But now what's being asked is master's degrees from international students for the Okanagan, so 77, and for the Vancouver campus, which is 905. So how do you deal with those numbers? You'll have to figure that out. Check the notes. What is the probability that an Indigenous student received an undergraduate, a master's, or a PhD degree from the Okanagan campus out of all the graduates? So now we have 3 calculations involved. And once again, the denominator in this is the same. It's 14,793. But we're wondering, oops, I got to go back because my memory is failing me. Okanagan, undergraduate, master's, PhD, Indigenous students. So the values we're talking about are here, here, and here. And what do you do with those values? The final question asks, what is the probability that a graduating student is international or getting an undergraduate degree at the Okanagan campus, or both, out of the 2019 graduates at UBC. So we're asking, out of all the international students, right? Or is an Okanagan, let me refer back to that, or undergraduate degree at the Okanagan campus. So undergraduate degree at the Okanagan campus, or both, right? So it was international. Ooh, that's a tricky one. Wait. International or undergraduate degree at the Okanagan campus. So there is an intersection, right? So this is the denominator. There's the total number of international students. There's the total number of undergraduate degrees. Now, what do we do with this number? This intersection. You guys need to figure that out. So that ends part A. Now let's move on to part B. So part B, we're going to use a binomial calculator. There's our binomial calculator. And we're going to input some data. And the data is as follows, right? So we've got these 3 cherry farmers on different land with different climate characteristics. And the first one's named Whiteley. Second is Smith, and the third is Wheelers. And a killing frost in Whiteley's land occurs 3 out of 9 years, so 0.33333. A killing frost on Smith's property is 1 out of 12 years, so that is clear. 1 divided by 12 equivalent to 0.08333333. And then Wielders is 1 out of 8. 1 divided by 8, which is 0.125. So let's figure out the first one. Do it together. So in our calculator, we're interested in a 5-year period, so change the n to 5, if it isn't already 5 already. And we want P, the probability of the event occurring, which is frost, to be 0.3333333. And there, the probabilities are displayed for the particular number of events. So for 0 frosts out of 5 years, that occurs roughly 0.13168. 1 frost in 5 years, 0.32921. 2 frosts, same value, 3 frosts, 0.164609. 4 frosts, 0.0411522. And then 5 frosts, 0.00411155. So it's 5 out of 5 years with frost. So you'll put those numbers in the table, right? So these probability values, we can go copy. I don't know what's going to happen. Paste special. Oh, there's the values, right? So you'll do that for all 3 farmers, and then it's asked. Whiteley wants the potential of having killing frosts 3 or more out of 5 years to be less than 25%. So 3 or more, that's these values here. Are those, when you add those up, are they less than 25%? And you figure that out. Same approach is used for Smith and Wielders. So if it is less than 25%, he should plant cherries, because the actual percentage is whatever this total is relative to 25%. Now the other farmers, they have different conditions, right? 2 or more out of 5 years to be less than 20%. Here for Wielders, frost 2 or more out of 5 years to be less than 10%. So you're going to have 3 different situations you need to interpret. Okay, part C. So I'm going to get rid of the binomial distribution calculator. And now you can see in Excel here is a Poisson calculator. And the raw data is here. So this data was collected from this graph. So the graph shows the touchdown locations for tornadoes in Illinois, and each square was evaluated to count how many tornadoes touched down in it. And it was discovered that there were 4 cells with no tornadoes, 19 with 1, 2 with 17, and onward. Now we need to use the Poisson calculator to determine whether or not this pattern that's displayed here, this observed pattern, is it close to the pattern that would be generated if we had a random event, a random situation. So I can copy and paste those values, put them into the observed frequencies, and totals are calculated out, observed probabilities, and then expected probabilities. So expected is the red line, the blue line is observed. Are they similar to each other, right? Or are they drastically different? You'll need to interpret that and then answer the questions that are associated with this in question 8. So are the observed and expected probabilities similar? Explain your significance of your findings. How do these results compare to the analysis of tornado patterns in Colorado described in lecture? So in lecture, we examined we examined Canvas, Colorado, and so go back to the lecture notes, read what it says, and then apply it to this question. The final probability question, part D, uses the normal distribution. And so what we have is a 121-year record of June 29th maximum temperatures for Kamloops, British Columbia. On this graph, all but the last year, 2021, is shown in a histogram, and we can see that it has this bell-shaped pattern with a mean somewhere in around 29 to 26 degrees, somewhere in there. In fact, here's the mean. The mean was calculated to be exactly 26.2, standard deviation 5.297. Now you're going to use those values to answer the following questions, and you need to use a table, a normal table, also to aid in this. So your questions are going to be answered with one or two formulas that were given. So there's the formulas that are available to solve for Zi or to solve for Xi. So the first question, what is the probability of Kamloops having a June 29th maximum temperature that is greater than 20 degrees? So you're calculating out the Zi for that. Input in here the mean 26.2. Your Xi is 20. Your standard deviation, which is 5.279, and you'll calculate a Z value and an associated probability. And you want to know what's the probability of having a temperature greater than 20 degrees. So you'll be calculating out what the probability is from the left-hand side to 20 degrees, and then you need to figure out what the probability is from 20 degrees to the end of the right side of the normal distribution. Similar question to 9 is 10. So now you put 36 degrees Celsius in there. And the question asks, what is the probability of Kamloops having July 29th maximum temperature that is higher than 36 degrees Celsius? So show your calculations, and it'll be this, a small value. 11, what is the probability of Kamloops having a June 29th maximum temperature that is between 24 and 29? So it's two separate calculations, one for 24, one from 28, and then you're going to subtract one from the other to figure out what's in the middle of the distribution. Question 12, what is June 29th maximum temperatures, or what June 29th maximum temperature would occur in a 1 in 100 year? So now you use this other equation. So you put your standard deviation in, your mean, and then you determine Zi from this 1 in 100. Now it's not 1%. Remember, the Zi is going to be half of 1% because it's either side of the curve. And then finally, question number 13, you'll go back to the first equation, and you'll figure out how rare was June 29th, 2021, when maximum temperature of 47.3 occurred relative to the 120-year record, the 120 years prior to that event. And you'll be surprised. It was very, very rare. So that's Lab 4.